In today's class, we will discuss Lagrange's linear partial differential equation. Its standard form is PP plus QQ equal to R, where small p and small q are dou z by dou x and dou z by dou y, with capital P, capital Q and capital R are functions of x, y, z. So once if the equation is in standard form, we can solve it with the following working rule. First step says that write the subsidiary equations or auxiliary equations, and these are given by these three ratios: dx by p equal to dy by q equal to dz by r. Now solve these simultaneous equations to have two independent solutions, u of xyz equal to c1 and v of xyz equal to c2. So keep this in mind, two independent solutions. That is, if this is the solution obtained by dx by p equal to dy by q, this is the solution obtained by either considering dx by p with dz by r or dy by q is considered with dz by r. But don't consider dy by q equal to dx by p. So once if you have considered dx by p equal to dy by q, that is done. So don't consider the same ratios by swapping the position to find the value of v. So that is what this is saying. Once if it is done, you can write your complete solution as phi of u comma v equal to 0, and nothing wrong if you write phi of v comma u equal to 0. Or you can also put this in one more form called u is equal to f of v or v is equal to f of u. But sometimes what happens, it is not possible for us to find the values of u and v by using these three ratios. In that case, we are supposed to extend our auxiliary equation by using this following property of ratios. That is, if a by b equal to c by d equal to e by f is there, then we can note that this is further equal to AL plus CM plus EN divided by BL plus DM plus FN. How we got this? This is obtained by multiplying and dividing by L to this, multiply and divide by M to this, multiply and divide by N to this, and add the numerator expressions and add the denominator expressions. You can note that the value of this ratio or value of these ratios is exactly same as value of this ratio. And this is quite useful for us when it is not possible for us to find u and v by using only these three ratios. One point. And the second point is, if you consider a by b equal to c by d, and if it is equal to e by 0, then it doesn't mean that the value of c by d is becoming infinity, because we are claiming that a by b equal to c by d. With that we are saying that these two are carrying the finite values. These ratios are giving the finite values, means this is not becoming infinity. Instead we claim that a is directly proportional to 0 and we write the value of e is equal to 0. So please keep these two things in your mind. We'll just come back to this one whenever it is required. Now let me try to understand how we solve the Lagrange's linear partial differential equations by using the following examples. Let me consider my first example, xp plus yq equal to z. It is definitely in standard form, pp plus qq equal to r. So we can write our auxiliary equation dx by x equal to dy by y equal to dz by z. Now consider the first two ratios, and you can note that when you consider the ratios, we are expecting they are in variable separable form or integrable form. So is it in variable separable form? Yes, it is function of x. 1 by x is a function of x multiplied to dx. 1 by y is a function of y multiplied to dy. So which means that these two are in variable separable form. We can integrate this one to find my first function. What is integration of 1 by x or integration of dx by x? That is given by log x. So our integration, this gives log x equal to log y plus log c1. So we know that log a minus log b is nothing but log of a by b. So this one is log of x by y equal to log c1, which says x by y equal to c1. That is our first solution, u equal to c1. And considering dy by y equal to dz by z, it is once again variable separable form. function of y into dy equal to function of z into dz. Just like the previous case, it's just integrated and simplified by using the logarithmic property. You will get y by z equal to c2, that is my v equal to c2. So I can write my general solution, that is phi of u comma v equal to 0 or u is equal to f of v. But please keep this in mind, I already explained you people, if you consider the same ratios by swapping the position, you will get the answer as y by x is equal to some c2. In that case, if you write phi of x by y comma y by x equal to 0, your answer is wrong. So this cannot be considered as the solution for us, because these two are not two independent solutions, because we've obtained by the same two ratios. Okay. So my next question is, sir, is that means is this the only possible solution for this equation? The answer is no. You can find some more solutions, some more possibilities, and for that, if instead of that one, you can note that if I consider dx by x is equal to dz by z, and it is once again in the variable separable form, so on integration you will get x by z is equal to constant. Now with these three possible solutions we have, I can write my solution as phi of x by y comma x by z equal to 0. That is, I am combining these two possibilities, these two solutions. Otherwise, I can combine these two to write my solution. So all the three answers are right. Now it is left to you people which one you are writing in the exam. You can note that if you just eliminate the arbitrary function from this, you will end up with the same partial differential equation for all these three solutions. And keep this in mind, these are not the only three possible solutions for this. You can have some more. So if that is the case in the exam, are we interested in finding all the possible solutions? No. In the exam, you just find u and v, one u, one v, and just put them in this expression phi of u comma v equal to 0 to write your complete solution, and that is fine for us. Okay, let me try to understand it's better through the one more example. It's in standard form. Write your auxiliary equation. Now consider the first two ratios. Here z cancels, y square comes here, x goes to the numerator here, and even this x comes there, so that becomes x square dx equal to y square dy. You can note it is once again in variable separable form. Function of x into dx, function of y into dy. Go for the integration. That gives x cube by 3 equal to y cube by 3 plus some constant divided by 3. Multiply throughout by 3. And your solution is x cube minus y cube equal to c1. This is your u. Now let me choose this first ratio and the third one. That gives y square will cancelled, z comes here, x comes here. So it is x dx equal to z dz, and we know integration of x is x square by 2, integration of z is z square by 2 plus constant by 2. So one more solution is what? X square minus z square is equal to constant. So then what is our solution is? Phi of x cube minus y cube comma x square minus z square equal to 0. Otherwise this is equal to function of this, or this one equal to function of this. Okay, it is once again very simple one. Okay, have a look at this one. This is not in the standard form, and it is not in the form of pp plus qq equal to r. First multiply this left hand side expression and put it in that form, and that gives this equation. It is in standard form. Write your auxiliary equation. But I think people can note this negative sign. So see, the standard form is pp plus qq. If this expression p or q carries the negative sign with this, that should be considered here also. Okay, so with that, so now if I consider the first two ratios, here z square plus xy cancels, z cancels, we get just dx by x equal to minus dy by y, variable separable form, integrate, simplify, log a plus log b is log of a into b, that gives xy equal to c1. That's fine. And let me consider these two expressions are these two, both are fine. Now I'm considering this first ratio and the third ratio. But you can note that we have got dx and dz, but here y is there. We cannot handle this y. So we need to express it in variable separable form. So what should be done? You can note xy equal to constant here. Just substitute that here. And you will get the expression only in terms of x and z. And just check out, is it possible to put it in variable separable form? Now I am taking x power 4 to the left hand side and the expression to the right hand side with x is left leaving here itself. That gives x cube dx equal to z cube plus zc1 dz. Integrate this. X power 4 by 4, z power 4 by 4 plus c1 z square by 2 plus some constant c2 by 4. Multiply throughout by 4 and take these two expressions to the left hand side and substitute the value of c1. That gives v equal to constant. Once if it is done, you know how to write your complete solution or the general solution. Now have a look at this example. This example is in standard form. This is small p and this one is small q. Write the auxiliary equation and observe the first two ratios. They are fine. Here z will get cancelled. Directly we will get the variable separable form. Integrate, simplify. So x by y equal to constant is your first solution. Now to have the second solution, now if I consider the first ratio with the third ratio, here x will get cancelled, z comes with dz, that's fine, but y comes with dx, that is not possible. We cannot integrate y dx because it is not in the variable separable form. The same problem happens with this. Y will get cancelled. We will get x dy equal to z dz. X dy cannot be integrated once again because it is not in variable separable form. In such kind of situations, we are supposed to choose the multipliers and maximum number of times, and whenever it is possible for us, we will try to choose the multipliers in such a way that denominator becomes 0 and numerator reduces to the integrable form. So right now I will choose this multipliers y, x minus 2z. So with this, let me just see what happens to the denominator. It is x, y is multiplied to this. Here x is multiplied. In this case minus 2z is multiplied. So minus 2xyz. So this will get cancelled. Denominator is becoming 0. That's fine. Now what about the numerator? Is it in integrable form? By looking at this expression, we feel like it is not in integrable form because it is y dx and this is x dy. But if you just observe it carefully, this is nothing but differentiation of xy. That is, differentiation of xy is nothing but what? X into differentiation of y plus y into differentiation of x. So that is differentiation of u into v. Product rule is used here. So which means that this can be rewritten as d of xy minus 2z dz equal to 0. So now this is in the form of 1 d xy is taken as u. Integration of 1 du is what? U. U is xy. That is what written. So on integration, this gives xy minus 2 times z square by 2 equal to constant. That gives xy minus z square is equal to c2. So our general solution is this. Phi of x by y comma xy minus z square is equal to 0. Now the question is, so can we put this set of multipliers in different form? Yes, it is possible. If I just multiply throughout by the negative sign, minus y, minus x, 2z, these two are exactly the same multipliers. If you use it, we will end up with minus xy plus z square equal to constant. That is not different from this one, because when you take the minus in common, that becomes minus c2. Minus c2 is one more arbitrary constant for us. Or I can divide this throughout by z. So even that one represents the same set of multipliers, like y by z, x by z, minus 2. Otherwise, I can divide throughout by x, like y by x, this is 1, minus 2z by x. All this represent the same multipliers. Okay, and don't treat them as different set of multipliers. Okay, I hope you people are comfortable with this. So we'll just, as we go further, as we discuss some more problems, you people will be more clear with this. Let me consider my next example, and it is in standard form. Write your auxiliary equation. But you can note that we can't find even single function u, so directly by completing any two ratios. So what can be done here? So choose the multipliers, no options. Now observe the denominator carefully. If I just add them directly, so plus y minus y cancels, minus z plus z cancels, minus x plus x cancels, which means that what is my first set of multipliers here? 1, 1 and 1. So that will makes denominator 0, and look at the numerator. Is it in the integrable form? Yes. This is 1 dx, 1 dy, 1 dz. Integration of 1 dx is what? X. Integration of 1 dy is y. Integration of 1 dz is z. That is equal to constant. So this is my first solution. Now the question is, what about our next set of multipliers? For that one, this is what I am doing. I am choosing x, y and z, because x dx plus y dy plus z dz is integrable form. So if I choose x here, this becomes xy minus xz, and choosing y, it is yz minus yx, and by choosing z, this becomes xz minus yz. So you can note xy minus xy cancels, minus xz plus xz cancels, plus yz minus yz cancels, which means that I can choose my next set of multipliers as x, y and z. With that, your denominator is 0 and numerator is in integrable form. Variable separable form is there, x dx, y dy, z dz. Integrate this. X square by 2 plus y square by 2 plus z square by 2 equal to constant by 2. My solution is x square plus y square plus z square is equal to constant. So now this is what my solution is. Further, in this case, it need not be x, y, z. I have told you people already, you can also choose minus x, minus y, minus z. You can also choose x by z, y by z and 1. That is also fine. Okay, let me take up next problem. And this one is exactly similar to the previous one. Only difference is in this place we have got x square, here y square and here z square. Okay, write your auxiliary equation. And if you just observe it, you can take that, if you know, you can note that if you take off x from this one, y from here, 1z from here, it will be in this form, xy minus xz, because 1y is taken here, yz minus xy, and this is zx minus yz, and this will get cancelled to make the denominator 0, which means what should be done here? I have told you that you should take off x from here, so divide it by x, divided by y, divided by z, which means these are my multipliers. With that, we get 1 by x dx plus 1 by y dy plus 1 by z dz divided by this expression. We already proved it is 0. So numerator is equated to 0. And is it an integrable form? Function of x into dx, function of y into dy, function of z into dz equal to 0. Integrate. And it is log a plus log b becomes what? Log of a into b. So it is log a plus log b plus log c, that gives log of abc, that is equal to log c1, that gives xyz equal to c1. Okay, in the same problem, instead of choosing this multipliers, you can also choose z by x comma z by y comma 1, even that is also fine. Now further, if you just divide throughout, if you divide this by x square, this by y square, this by z square, even that will be even in that case the denominator will be 0 if I just add them. So I will choose 1 by x square, 1 by y square and 1 by z square as my multipliers to have this expression, and integration of 1 by x square is minus 1 by x, and this is minus 1 by y, this is minus 1 by z, that is equal to minus c2. So my solution is 1 by x plus 1 by y plus 1 by z equal to constant, and you can write your answer. Okay, let me have a look at our next example. Z times x plus y p equal to z times x minus y into q equal to x square plus y square. Write your auxiliary equation, and Now I will choose my first set of multipliers as this x minus y minus z, and we know it is equivalent to we can put it in many other forms, minus y plus x z and all, and you can note that with this set of multipliers this denominator becomes 0, or you can also choose denominator becomes 0 and numerator is definitely in integrable form, integrated, and this is what your first solution is. Okay, so now I will choose in my next set of multipliers. Okay, yeah, so as I explained here, so it is minus x plus y plus z is also same, or you can also put it as x by z comma minus y by z comma minus 1. Even this represents the same multipliers. Okay, with this y x and minus z, we know that y dx plus x dy is integrable now, so that is what I'm choosing this time, and with that, so denominator becomes 0, you can just check out, and numerator is equated to 0, so this becomes d of xy minus that dz equal to 0, integrate, that will give us the answer. This is my solution. But in this example, I need not to go for two set of multipliers, so only one set of multipliers is enough, because if you just observe these two carefully, here zz cancels, and on cross multiplication you will get x dx minus y dx, that is equal to x dy plus y dy, and if I take this y dx to the right hand side, it becomes y dx plus x dy, and we know that it is integrable form, that can be written as d of xy. So now on integration this becomes x square by 2, this is xy, this is plus y square by 2 plus c by 2, and multiplying throughout by 2 we will get this one, x square minus 2xy minus y square is equal to constant. You can use this as one solution, and instead of choosing two set of multipliers you can go for one set of multipliers in this example. Okay, have a look at this one, and let me write it in standard form. It is already in standard form. Write the auxiliary equation. And in this example, you can note that if you try to make the denominator 0 by choosing the multipliers, so you won't get the numerator in integrable form. Now, if we just observe them closely, and from these two, if I take the difference between these two, you can note that dx minus dy divided by x square minus yz minus y square plus zx, and x square minus y square is nothing but what, x plus y into x minus y, and from these two z is common, and I can note x minus y is common here, that gives x minus y times x plus y plus z. But you can note that these functions are in cyclic form, so x square minus yz, and they're you're just moving the values of x y z here in cyclic form, that gives y square minus zx, and z is pushed here, so z square minus xy. So which means definitely you can note, even if you consider dx minus dz, it will be x minus z into x plus y plus z, or if you consider dy minus dz in the numerator, it will denominator gives y minus z into x plus y plus z. So which means something which is there in our favor. So what I'm doing now, I'm choosing the multipliers as 1, minus 1 and 0, that is 1 dx minus 1 dy, that gives dx minus dy, with with 0 dz becomes 0 there, and 0 1 minus 1 to have dy minus dz, and minus 1 0 1 to have dx minus dz, or dz minus dx. Yeah, so this is what we have here, and you can note that dx minus dy divided by x minus y is integrable form. And please keep this in mind, don't cancel this x plus y plus z, because it is present in the denominator of all the three expressions, because these three auxiliary equations are equated to these three ratios. Okay, so these three ratios are equated to these three ratios. Since the denominator is not carrying x plus y plus z in these cases, I cannot cancel x plus y plus z from these, so we are supposed to keep them as it is. Now what I will do, I will consider first two ratios, and from that x plus y plus z cancels here, we get d of x minus y, that is for nothing but what, dx minus dy, and this one is dy minus dz divided by y minus z, and you can note this is in the form of du by u. Integration of du by u is what, log u, and that gives log of x minus y equal to log of y minus z plus log c1. Log a minus log b formula is used, so that gives x minus y by y minus z equal to c1. Now you use either these two ratios or these two ratios to have one more solution. Right now I am using the first and the third ratio here to have the solution x minus y by z minus x equal to c2. So now from these two we can write our general solution, that is phi of x minus y by y minus z comma x minus y by z minus x equal to 0. Okay, I hope you people are comfortable with this method now, and for you people to practice I'm just giving you these examples, so please try to work out from your side. Thank you all. If you have any doubts, so please call us.